Hello everyone. Hopefully you have your notes in front of you, and we are now prepared to start talking about our next set of hypothesis tests. So we're starting chapter 12. Here's a summary of the things that we've learned so far. So we've been talking about doing significance test on one population. So we start with the population and we want to do a test on the means. This is what we covered so far. If we're testing a mean, we have two choices, either a z-test or a t-test. And today in this chapter we're going to start talking about proportions. If we're testing on a proportion, there's only one option, it's a z-test. And finally a variance, which if we're testing a variance, we're going to do something called a chi-square test, which is what that little symbol is. And that we'll learn in chapter 13, so you don't have to worry about that today. Today is going to be all about the middle column here, about proportions and z-tests. The goal of this exercise is to estimate or question or compare population proportions. So if you're given a number of observations n and a number of successes x and a sample proportion p hat, our good old friend the p hat is back, and we would like information about the population proportion rho. So no more, when we're talking about proportions, we're not going to be talking about x bars or mu's anymore. We're going to be talking about p hats and population proportions, which are the big P, the rho. For a one-sample z-test for a proportion, the conditions are, if you remember this from chapter 9, the population must be at least 10 times as large as the sample, and the population must follow a normal distribution, which means n times p has to be greater than or equal to 10, and n times 1 minus p also must be greater than or equal to 10. So those are the two conditions that must be met in order to do a one-sample z-test for proportions. The z-test statistic, this is a formula that you're going to want to write down. It should look it should look a little bit familiar. It's got parts of things that we've seen before. The z-score is given by p hat minus the null hypothesis for p divided by the standard deviation. This is the formula for the standard deviation of a proportion problem. Remember this from chapter 9? And then over here we have standard error, which we use when we do confidence intervals. All right, so SE is the standard error. Once again, that is nothing more than the standard deviation of a sample. For a confidence interval, same conditions for a confidence interval as there are for a z-test. The population must be at least 10 times as large, and the population must follow a normal distribution, meaning n times p sub 0 must be greater than or equal to 10, and n times 1 minus p sub 0 also must be greater than or equal to 10. The formula for a confidence interval is given right there, and basically it is as a mean. It's just replacing, instead of x bar, we use p hat. It's a z star, because that's our only choice for proportions. And instead of the standard deviation divided by the square root of n, it's the standard deviation for a proportion problem. All right, so here's an example. The present packaging system produces 10% defective cereal boxes. Using a new system, a random sample of 200 boxes had 11 defects. That's a pretty good average. It's 5.5%. Does the new system produce fewer defects? Now remember, this is one random sample. So random samples have a lot of variability. The question is this evidence enough to say that the new system is better? So what we're going to start off with, this is a one proportion z-test because we're dealing with a percentage. The null hypothesis would be that the population proportion is 10%. The alternate would be that the population proportion is less than 10%. We want to test at a 5% alpha level with a sample size of 20. Here is our critical values. Right, here's our picture. This is the 5%. 5% is a 95%, so we can look down our 90%. Sorry, it's a 90% area. So we can find the z critical based on a 90% confidence interval. Based off of that, then, we can do a test statistic using this formula. So p hat was what was given to you. It was 11 divided by 200, 11 out of the sample of 200, minus our null hypothesis of 10%, divided by, you use the null hypothesis of 10% to calculate your standard deviation, and you get a z statistic of negative 2.12. That is obviously less than our negative 1.645, so our p-value is going to be much lower than 5% because our test statistic is going to be lower than negative 1.645. So we're going to reject, and our conclusion then would be there is evidence that the new system is less than 10% defective. Right? That was our alternate. Is it less than 10%? We have a probability of less than 5 that 11 out of 200 would occur. That is evidence that it is, in fact, defective. All right, so here's another example. It says you're an accounting manager. A year-end audit showed 4% of transactions had errors. You implement some new procedures. A random sample of 500 transactions had 25 errors. Has the proportion of incorrect transactions changed? And we're testing at the 5% level. So here's a one-sample z-test solution. Our null is that the null is 4%, right? Because we're testing at 4%. The alternate is, has it changed, right? We want to know, is it no longer 4%? We're testing at an alpha level of 5%. We had a sample of size 500. Here's our picture. All right, so if we're testing at a 5%, that means we have 2.5% on the left and 2.5% on the right. So that way we have 95% in the middle. You can look in your test booklet and you can see that 95% in the middle is a 1.96 test statistic, or a z-critical score. Use our formula that I just gave you to calculate the test statistic, the z-score. So our p-hat, we had 25 out of 500, minus our alternate, divided by, or minus our null, sorry about that, minus our null, and then we're dividing by, use the null here for 0.04, and 1 minus 0.04, and we get a test statistic of 1.14. That, if you look at your list, at your picture here, 1.14 would be somewhere in this area, right, somewhere in here. So based off of that then, wow, I don't know what's going on my computer. Get rid of that stuff, sorry. Okay, give me a minute while I'm having technical difficulties here. Based off of that, our decision is we would fail to reject, or we would not reject at the alpha 0.05 level. And our conclusion then is that there is no evidence that the proportion has changed. Right? So if you fail to reject, we say there is insufficient evidence to conclude that the proportion is no longer 4%. It is not equal to 4%. All right, so here's example number 3. For example number 3, in a random sample of 600 residents from the state of Nevada, 450 are classified as overweight. We want to determine a 95% confidence interval for the proportion of Nevada residents who are overweight. And we want to know, does this survey provide evidence at the 5% level that Nevada residents differ from the national rate of 71% overweight? Okay, I would like for you to do that problem using the formulas and the procedures that you saw in example numbers 1 and 2. See if you can answer that question, and we will talk about it tomorrow in class. And then here's example 4. Same thing. Read this question, answer it on your paper, and then tomorrow when you come into class, we'll be able to start from there and see how you did on answering these questions before we do any more practice problems. So that's it. That's all I have. Hopefully you took some good notes. And tomorrow when you come into class, I'll answer any questions that you may have, and we will do a couple more examples on one sample z proportions. Thank you, and have a good night.